Hello and welcome to CPE214 Signals and Systems. My name is Sanditam Prom-on. Today I will give you the video lecture of Lecture 2, Signals Representation and Time Domain Operation. Let's begin. We can define signals as measurable quantities that convey information about phenomena and vary with certain independent variables. For example, time. These independent variables can also be other things like if it is about spatial coordinate, then it can be x and y and so on. We'll talk about these independent variables later on. The terms of signals can include many things actually in many terms. For example, it can be electrical signal if we are talking about voltage and current measurements. It can be acoustical if we are talking about speech from microphone. It can be the visual signals if we are talking about camera, the digital camera photo. It can be the radio signal if we are talking about something like Wi-Fi or the radio wave, or the digital. You may have heard the digital TV phenomenon earlier. It can be geophysical like GPS measurements, or biological like protein or blood sugar measurements. So you can see that these these quantities contain certain information in it, and by representing them as signals, we are able to use mathematics to help analyzing or doing tasks related to them. Signals can be represented as functions of one or more independent variables. These variables can be either continuous or discrete. This course will focus mostly on signals with time as independent variables because they are the most basic one-dimensional signals. Later on, you may have encountered different types of signal that have more than one dimension. For example, if you work with image, those are two-dimensional signals. For video, the video signal is three-dimensional, containing the spatial location and time as the third dimension. Mathematically, for this course, which will use only the time as independent variables, we denote the signals by using a symbol and a parenthesis with an independent variable inside. For example, we can write x and a small t in the parenthesis to denote the continuous time signal. In the contrary, for y and the square bracket and n to denote the discrete time signal. This is just like a function. That is, x is a function of time and y is a function of n. The value of x varies with time t, and the values of y varies with the index n. So this parenthesis is not the algebraic parenthesis that you encountered earlier, that you can multiply the constant or the value inside the parenthesis. This is different. This parenthesis denotes the function. Signal can be many types and contain different types of information. For example, the acoustical signal that you generate when you play the guitar. It contains the quantity that you can measure is a sound pressure. The information inside that variation is the sound itself. Signal can be two-dimensional, like this geophysical signal of atmospheric pressure. The quantity that you measure here is the atmospheric pressure, represented by numbers. Here, these numbers represent this contour represent the line that have equal atmospheric pressure. So this is 1008, and this one is 1010, this one 1012. So this is just like a mountain. The information that is contained in this signal is something like weather and maybe the storm path. Independent variables of these signals are the latitude and longitude, and the measured quantity is the pressure. This is an image which is a two-dimensional signal. The quantity that is measured is the light. So you see light in color here, and information in it may be scenery, object, persons. And when we look at it as a signal, it is just like I, X, Y here. X and Y are the X and Y coordinates, and I is the measurable quantity, the intensity. We can also think of something that is so far away from us, like finance as a signal. In terms of finance, we can measure the stock value as the quantity, and the information in this stock value variation would be something like company values. Like this example show the variation of Facebook stock price over time. If we can think of it as FT, the stock price as a function of time, and you will see the variations just like this. We can describe signals using different ways. Here I show you three different ways, three basic ways that you can do it. First, by represent it using function. For example, you can write xt, assign if xt is in the form of sinusoidal, you can write that xt equals psi t. You can write a signal as a sequence of values. Like in this example, xn is a sequence of 0 and 0 until the time index 0, and then 1, 4, 6 with the time index 1, 2, and 3, and 0, and so on. You can also write the graph of the signals, which I will show you the components inside the graph later. This graph is a graph of discrete time signal. Each stem here represents signal values at each time point, starting from -5, -4, -3, and so on. The x-axis is the time value axis, which is the axis of an independent variable. The y-axis is the signal value, the value of signal xn. And we have the middle line here, also the x-axis at xn equals 0. Each stem is a signal value, so this point is x at the time -3. We write it as x and -3 in the square bracket. This is x1, x and 1 in the square bracket. You can see that here x -3 equal -1 and x1 equal 1. The value of x1 is 1. And x4, the value of x4 is also 1. We can write signal as functions. For example, this signal has 3 intervals. The first interval, which is the interval that the time is before 0, and the second interval, the timing is between 0 and 1, and the last interval when the time is more than 1. So the graph of this will contain 3 intervals. The first interval is the values of the signal is 0, the value of xt is 0. The second interval, the value will be sinusoidal sine 2 pi t. So this is sine 2 pi t when the time is 0 to 1. And the last interval, when time is more than 1, the signal value is also 0, just like this. Let's look at another example for the discrete time signal. This signal has 3 intervals. The first interval, the value of the signal is -2, and it lasts until the time index n less than -2, which means that n start from -infinite, and the value always be -2 until it reach the point where n equal -3. Then at the time -2, xn equal n and lasts until n equal 2. And this is n less than 3, which means n equal 2. So from n equal -2 to n equal 2, xn equal n. And when n is more than or equal to 3, n equal 2, we can write this graph, this signal as a graph as follows. That the first period starting from -infinite until -3, xn equal -2. And then from in the second interval from -2 to 2, the value of signal equal n. And in the last part, the value of signal equal 2 to from 3 to infinite. We can write signal as a sequence of value, but please note that to write it as a sequence of value, you need to also specify the point at n equals 0 as a pivot point, so that you will know the indexes of each point that in the sequence that you write. For this one, the ellipses denote the value that repeats itself, so it should be 0, just like this, and this is also 0. So what we have would be 0, 0, and then becomes 2 at time equal -1, become 1 at time equals 0, and become 2 at time equals 1, and then 0, 0, and so on. That's it for how we can write signals as a function, as a graph. Now let's look at what we can do with the signals. We can transform we can definitely multiply the signal with some constant and get the higher values of the signals. That is the basic idea anyway. But we can also digging further into the independent variables and doing the transformation, so that the signal would be shifted, flipped, or either scaled, depending on the types of operation that we choose. So let's first look at the first operator, time shift. Suppose that you have the signal xt look like this. That is, it becomes 1 at time between 1 and 3. The signal xt minus 1 would be the signal xt like this, shift to the right by 1 unit. So now it starts from 2. I write yt here so that you will not be confused by the operation. That is, this is the signal yt equal xt minus 1, the new signal yt. So the shifted version of xt minus 1 looks like this. This process is also called time delay, because to delay the event of the signal by a certain amount of time. Let's look at another example down here for the discrete time signal xn. Xn here has a value of these 3 stems. If we have a signal, another signal, if we perform the time shift operation and get a new signal yn, which equals xn plus 1, the graph of signal yn will look like this. That is, it is the xn shifted to the left by 1 unit. We can also reverse the time with respect to the origin, with respect to the time equals 0, by applying the minus operator into an independent variables. So if xt, just like in the previous example, look like this, for the signal yt equals x minus t, would look like the origin signal xt, but flip it to the negative side with 0 as the pivot point. For down here, for xn, look like this, minus 1, some value, and 1. The flipped version of this, or the time reverse version of this, would be yn equal x minus n. That will make the minus 1 here, instead of being at the minus 1 n equal minus 1, it will be at n equal 1, and this stem from n equal 1 will be reversed to n equal minus 1, but the value at n equal 0 will stay at that point. We can perform the time scaling by multiplying an independent variable with some constant. The equivalent of this operation is like when you watch the movie and then you slow it down or watch it in the fast forward manner. That is also the process of time scaling. So if the signal that we have here look like this, xt as a triangular signal, then if you multiply an independent variable t with a constant of 0.5, you get the lengthened version of the original signal. So this is the signal yt equal x 0.5 t. Yt when t of yt equals 0, you get y0 equals x0. If t here equals 1, then you get y1 equal x 0.5, and if y equals 2, you get x1. That means y2 here at this point equals x1, which is the peak of the signal xt, and y4 will be x2, the point where the signals reach 0. So it is the lengthened version of xt when you multiply with a constant that is less than 1. The same things for dt signal, but instead of having the lengthened version, you get a kind of a repeated values, or the upsampling version of that signal. Signal can be periodic, meaning that it repeats itself with certain period. If, for example, the CT signal xt has repeat itself with a period of t, then xt will equal xt plus that period, meaning that if you comparing the signal with its shifted version by time t, it should be equal. That is the nature of the periodic signal. As shown here, the signal shown here is the triangular signal with a period of a. So when you shift this signal xt by a period of a, you should get the two signals that are equal. The same goes for this dt signal. Xn, if it is periodic signal, then it should have an equal signals at xn plus n plus capital N. And this n when it has a smallest value, we will call that smallest value a fundamental period, and it is the smallest positive value of either n or t that will hold this equation. So for this graph below here, the fundamental period equals 3 because this xn repeat with a period of 3. But you can imagine that you can add 6 to this, you can shift this signal by 6 and it still equals to the original signal. But since 3 is less than 6, and it also make the above equation valid. So 3 is the fundamental period. This is a different classification of the signals. The signal can be even or odd signals. And even signals will have certain characteristics which is different from odd signals. Even signal, for even signal, x minus t will equal xt. The flipped version of xt will equals to itself, meaning that it is symmetry to t equals 0. Same goes for this, xn equals to x minus n, symmetry at t equals 0. For odd signal, it will be anti-symmetry at t equals 0. That means x minus t would equals minus xt, and x minus n equals minus xn. You can decompose the signal into even signal or odd signals. And even signals can be calculated by combining the signal itself with the reversed version of the signal and then divide by 2. Then you get an even version of the signal. You can think of a signal, then you flip it and then add them together and then divide it by 2. You should get a signal that is symmetry to the time equals 0. You can calculate the odd version of the signal by subtract out of the original signal the flipped version of that signal and then divide by 2. You get an anti-symmetric signal, an odd version of the signal. This concept will be again mentioned when you learn about Fourier series, because they are very essential idea in that sense. Now I will talk about some basic functions that you can use to describe signals. But note that these functions can also be used to describe something like impulse response that you may have already learned, the representation of the systems. So they are very general functions, can be used to describe different things. We can use them to describe signals. We can also use them to describe function. So let's start with the basic unit step. Step means that you start from nothing and then jump to the value of something. So it's like on and off situation, like when you turn on the switch, when there is something turning on. So the signal ut, the function ut, will behave like this. That is, it is 0 when time t is less than 0, and it is 1 when t is more than 1. So there is a discontinuity at time t equals 0 here. That is, the signal jump from 0 immediately to 1. For the unit step of the discrete time signal, dt unit step, we use we use u to denote the unit step function. So ut in the CT will be the unit step function in the continuous time domain. In the discrete time domain, we have un, which equals 0 when n is less than 0 and equal 1 when n is more than or equal to 0. Meaning that if n is less than 0, then the value of un are all 0. But at n equals 0 and so on, the value of un is 1. The next type of basic function is an impulse function. In discrete time domain, it can be easily understood. In discrete time domain, we call an impulse as a unit sample. We use delta to represent that, to denote the impulse function. Delta n is the discrete time impulse or the unit sample signal, the unit sample function. The value of delta n equals 0 when n is not equal 0, and equal 1 when n equals 0. So the graph of this signal will look like this. That is, it has only one values at 0. The situation is a little bit different in the continuous time domain. You can imagine the unit impulse in the continuous time domain like when you kick the ball or hit something. Then the force that applied to that object will gradually increase to the peak and then decrease. So let's imagine that if we reduce the time of impact to be shorter and shorter and applying the same amount of force, then the amplitude of that force would be higher and higher. Just like if you hit the object with a very short period of time very fast with the same effort, then you get the higher amplitude. So in the continuous time domain, there we describe unit impulse with its properties. That is, in terms of amplitude, the unit impulse equals 0 when t is not 0. But we do not describe it as its amplitude, but we describe impulse as area enclosed by the impulse, the area under the curve of the impulse. That is, if you integrate from minus infinite to infinite of the impulse function, then you get it equals to 1. This represents the energy of the impulse, that it contains energy equal 1. We write a graph of this impulse function using an arrow, an upward arrow, and the number beside it as an area under the curve. This will help you to imagine the concept of unit impulse in the continuous time domain. If we think about this square wave, think about it that it must have an area under this curve equal 1. Then if you shorten the amount of time this delta t to be shorter and shorter, and if the delta t approach the values of 0, then what you have is that the amplitude here will have to increase to be infinite, and that is the impulse. And we use this upward arrow to represent it. There are certain relationships between unit step and unit impulse. I will talk about it in the discrete time domain first, and then the continuous time domain later on. So for the discrete time domain, delta n, the unit impulse, you can calculate the unit impulse by subtracting the unit step with the shifted version of the unit step, shifted version to the right. Then you get a delta n. You can also think of the discrete time unit step as the running sum of the unit sample, because we know that the unit sample has the value of 1 at n equals 0 when the independent variable of its function equals 0. Then it means that this delta k will be 0 when k equals 0. If we calculate the running sum of n from minus infinite to n, of k from minus infinite to n, then when n is less than 0 or in the negative values, what you have here is that the value of delta always be negative. But when n here is more than 0, then you can see that if n is more than 0, the running sum will pass the 0 values and pass the value of 1 of the unit sample. So the values of un will be 1 after n is more than 0. The unit sample function can be used to sample a value of a signal. If you multiply delta n with xn, what you have is x0 and delta n. So you can sample the values at x0 when you multiply the signal with delta n. The reason is that because delta n only has the value at n equals 0. So when you multiply it with any signal, only the value at x0 will be carried on to the multiplications. So in general, if we shift the delta by certain amount of n0, an arbitrary number, then you can think of it as a sample machine that when you multiply this delta n minus n0 to any signal, you get the value of x n0 that multiply out of that. For the relationship of CT unit step and unit impulse, we can see from this slide. Just like in the discrete time version, we can think of the unit step function in the CT domain as the running integral of the unit impulse, because when we integrate the function, we got an area under the curve. So if we integrate the area under the curve of delta here, delta tau, we would get the value of 1 if we pass through 0. So by integrating from minus infinite to t, if t is less than 0, the values of this function will be 0. But if t pass through 0, then you would get the values of 1. Okay, delta is also associated with un in this sense, that is, if you take a derivative of ut, if you take the derivative of ut, you would get delta t, because there is a discontinuity at t equals 0. The derivative will calculate something like the slope of the change. So since the slope there is infinity, what you have is just like the function delta t. Now, in the last part of this lecture, I will introduce you to the exponential and sinusoidal functions. This will be used later in Fourier's and Laplace transforms lecture. So let's consider a general terms of complex exponential signal. This signal xt equals c e to the at, or the signal xn equals c to the alpha n. Here c and a can be either complex or real numbers. Same goes for this c and alpha. So this complex exponential can be expressed in different forms. It can be this signal can be real and exponential, decreasing or decaying. It can be periodic, which means it repeats itself, complex exponential, or sinusoidals. It can also be general complex exponential terms. Let's look at it one by one. Let's look at them one by one. If a is a real number, is a real value, then you get a real exponential signal. When a is less than 0, what you have is a decaying signal. Because when a is less than 0, as t increase, this term will increase to minus infinite, making the whole term here approach 0. But if a is more than 0, when t increase, this term will be very large, and the exponential of this term will be a very large value. That is why you get an exponentially growth function like this. If the exponent a is purely imaginary, what you have is something like this, that is e to the j, which means that it is purely imaginary, and some value and a constant omega 0 t. This e to the j omega 0 t is a periodic function, which means that this equals to e to the j omega 0 and t plus capital T, the fundamental period. So we can use an Euler relation to decompose this e to the j 2 pi t. Let's say that we make the alpha 0, the omega 0 equals 2 pi. Two terms, the real term and imaginary term. Real term here equals cosine 2 pi t and an imaginary term of sine 2 pi t. So if we take only an imaginary term out and plot the graph of this imaginary term, let's say yt, and imaginary term of xt, then we get this sine 2 pi t. And the graph of sine 2 pi t looks like this. That it is a periodic of the fundamental period of 2 pi over omega 0. Here, let's further define some terms. That is, omega 0 here is an angular frequency, and t0 is the fundamental frequency on the fundamental period. In the last case, if a is a complex number, that is, it is not purely real number, or it is not purely imaginary number. If a equal r plus j omega 0, and if we plug this term into this equation again, we will have this is c e to the r plus j omega 0 t. And if we pull this, if we multiply t into this parenthesis and then pull rt into one term and r to the j omega 0 t into another term, we can do a decomposition just like in the previous slide. That is, one term is the real term and another term is an imaginary term. So if we take only the real term using the real function here, we will have this term equals c e to the rt cosine omega 0 t. Now, the cosine term indicates the oscillation of the signals, and this exponential term will control the rate of growth, whether it will be decaying or growing. If r here is less than 0, you will have an exponentially decay to the 0 values. If r is more than 0, then the function will oscillate and growing without bound. Okay class, this is the end of the lecture. If you have any question, please feel free to contact me via email or Facebook group. I will try to reply to your questions as soon as I can. Bye.